Thanks for the introduction. Thank you everyone joining our talk this morning. And I can't see you, but hopefully we can share this project to you virtually. And if you have some comments, questions, you can leave your questions on Slack. And today we're going to talk about one of a collaboration project with HPCC systems. And the aim of this project is we try to use deep learning techniques and to help us to understand how the people make decisions in finance. So this is a project we just started 1 year ago, and we got some support and sponsorship from HPCC systems. And also we would like to thanks for HPCC systems to invite us to give a talk on these seminars. The story behind this talk is about we already know a lot of data in financial industrial, but it's not much knowledge about how the people make decisions. There's a lot of economic theories and behavioral finance theories behind that, but most of them they are based on mathematical analysis. And we try to find the other ways, use a data approach to explore some ways whether we can do that in big data ways. So first of all, there's a lot of theories in terms of the financial markets. One of the very famous ones is the hypothesis of efficient markets. So traditional theories economics, they believe that the markets, in the market, people are rational, which means they will buy at a low price and will sell at a high price. But if this is right, and we don't have this financial crisis, also we don't have the bubbles, and so people, if they act exactly like rational models, and our market will be fully functional. But in realities, this is not the real case. And so it's another bunch of areas we call behavioral finance, because behavioral finance provides insight about the irrational part of human behaviors and use a lot of psychology explanations. And it will give us a very good explanation about all this kind of phenomena like bubbles, crises, and why the people don't follow the traditional classical economic models. In realities, the decision makings by human beings is largely affected by the psychology perspectives. And the people will believe they are biologically coded and to mimic the actions of a large group. So this is kind of DNAs in our genes, and we always want to follow the large group rather than small group. And this allows us to quickly absorb and react based on the intelligence of the others. And so this kind of very human behaviors, not only in finance but also in the other areas. And the people repeat what they are doing again and again. So we always kind of find some patterns in terms of the data, and especially in financial market, we're seeing the financial crisis happen again. Every 10 years, maybe we have a financial crisis. This kind of patterns, and also the people that making behaviors, this kind of thing, we found this happen again and again. And the questions behind that is how we're gonna find that patterns. Traditional study of behavioral finance, because we are based in mathematical institutes and math finance group in Oxford universities. And we have some colleagues, they are experts in behavioral finance, but traditional behavioral finance studies, and they study in last decade, they mainly focus mathematical models, and they use a lot of perspective series. I think Yuting will talk a little bit more about this one. And they try to find some explanations about how the mathematical model works and consistent with the psychology perspectives. But nowadays, the big data online and also in financial industries, especially in tradings, and provide us new opportunities. And so we can take advantage of the massive data set and in finance and try to investigate the insights from another dimensionalities and how the people behave in financial markets from data perspectives. I think that's the whole story behind this project. And we just started this project 1 year ago. It's still ongoing project, and we are sorry about the abstractive because this abstractive a little bit misleading because it's a kind of the description of our whole project, but this project is still ongoing. And so we'll cover part of this projects, but it's still ongoing and something still unfinished. So we don't have a lot of result to present. And I will hand over to Yuting, and Yuting will talk more about the ongoing work and what she's doing. And Yuting is founded by HPCC Systems, and he's a DPhil student working solely on this project.
Okay. Okay, thanks, Ning, for the introduction. I'm going to present our ongoing project on the mid-price trend prediction in limit order book. I'm going to introduce the background of this project, the limit order book data we use, our model and the baseline model, and the data preprocessing and the final results. As we're going to use the limit order book dataset for the mid-price trend prediction, we include information that much more than the series of price itself. I will explain why this additional information might be helpful. As Ning just mentioned, the efficient market hypothesis states that the asset price reflects all available information. An efficient market is defined as a market where there are a large number of rational participants actively competing to predict the future market values and individual securities, and where important current information is almost freely available to all participants. This leads to the situation that at any point of time, actual prices of individual securities already reflect the effect of information based on both events in the past and that market expect to take place in the future. In this view, it seems there's no need to involve information other than the price itself for price prediction. However, researchers have disputed this efficient market hypothesis both empirically and theoretically. Researchers in the study of behavioral finance states that predictable human errors in information processing will attribute the imperfection of financial markets. For example, in the prospect theory, this concept called certainty effect, it states that people tend to overweight outcomes that they are considered as certain and related to the outcomes which are just probable. And also, the reflection effect states that people tend to be risk averse when they have positive profits, but be risk seeking when they have negative profits in the market. If we have information regards to these biases, it could be helpful to add some explainability to the market prices. Some empirical studies found that, such as I show here, the low price to earning stocks have greater returns, and this also casts doubt on the efficient market hypothesis. So it could be helpful to to use more information than the price to predict the prices. The motivation of this project also comes from the observation that human traders receive various kinds of information, mainly visual, text, and other information. Visual information, for example, the limit order book that we're going to use, and text such as news and text from social media, and other information such as financial statement of a company. Like humans, it is possible for machines to learn from this kind of information and find patterns or knowledge that is consistent with human traders, or possibly could find new patterns that haven't been found by humans before. This project focus on the visual information part. The purpose of this project is about the predict the mid price from the limit order book datasets. Our problem is generally a financial time series prediction problem. Financial time series prediction is a widely studied research topic. Various methods have been proposed. This method can be generally classified in 3 categories: time series analysis, machine learning, and technical analysis. Most of the time series analysis approaches, such as autoregressive moving average and the sparse coding, captures the linear dependency of data. The machine learning methods such as SVM, random forest, and various kinds of artificial neural networks have been directly applied. Most of these methods can capture the nonlinear dependency of data. Technical analysis use technical indicators such as moving average and unbalanced volume for price predictions. These indicators of prices and volume, they are indicators of the prices and volume change. The candlestick pattern is also a kind of technical analysis tool. However, these methods have some shortcomings. For time series analysis, financial data usually have highly nonlinearity, but most of time series analysis approaches focus on linear dependencies. For machine learning, most of machine learning methods lack the explainability, and the direct application of some existing models may be not able to obtain good results. For technical analysis, the technical indicators are from past experience of humans, and there's no strong proof on what kind of technical indicators have strong prediction power. And we humans select these indicators based on our own experience, which might involve some bias and may not lead to good results. So how do we conquer these shortcomings? We are going to use large amount of information combined with the power of machine learning with some knowledge of features in the model design and add some explainability to the model. Our task is the mid-price trend prediction of limit order book data. I'll briefly introduce what limit order book is. In security trading, an order book contains a list of buy orders and sell orders. A limit order is a type of order to buy or sell a security at a specific price or a better price. A buy limit order is an order to buy at a present price or lower, while a sell limit order is an order to sell a security at the present price or higher. As you can see from this picture, the x-axis is the price. The green bar marks the level of sale orders, or to say the level of ask, and the purple bar marks the level of buy orders, or to say the level of bid. For the ask side, the higher the price, the higher the level, while for the bid side, higher the price, lower the level. For example, in this picture, the ask level 1 is the highest green bar, and the bid level 1 is the highest purple bar. The height of these bars represents the volume of at each price level. An order book is the list of orders that arrive in a trade venue, in particular the stock exchanges, and they used to record the interest of buyers and sellers in a particular financial instrument. The mid price is the average of level 1 ask price and the level 1 bid price. We are going to predict the trend of mid price, which has 3 categories: the up, stationary, and downtrend. We will specify the definition of these classes later. In this project, the data we use is a high-frequency lobster dataset. This dataset consists of 2 kinds of data: the limit order book data and the message data. Here are the examples of these 2 kinds of data. The 2 datasets are both based on order flows. As you can see, in the limit order book data, from the first column to the fourth column are the price and volume of ask and bid level 1. From the column 5 to the column 8 are the price and volume of ask and bid level 2, until the price and volume of ask and bid level 50. So this data set has 200 columns, and each row represents the prices and volumes that at the time a new order is placed. The message data contains information of each order. The first column is the time that the order is placed, in seconds from the midnight. The price and then the price and volume of the order. The order type here has 7 categories because it involves the hidden limit orders. And the direction here is just an ask or bid order. We are not going to use the message data now, but some information such as the time and the event time might be useful in future studies. Here are 3 previous works on the mid-price trend prediction of limit order book data. The first work in 2015 uses the SVM for classification. Besides the ask, bid price, and volume, they added some combinations of these row features as new features. For example, the means of prices and volumes. The second work used the same set of features as the first work. They use single layer feed-forward neural network to predict the mid-price trend. They generate an open dataset using the limit order book data from the Nasdaq Nordic stock market in 2010. We are going to run our model on this benchmark dataset as well. The third work did not add additional features because they use much more complex neural network structures than the previous works, so it could capture more complex nonlinear relations of the raw features. Our work also used neural networks, but our work is different from the third work in that we are using a simpler neural network structure but obtain better results. Also, we are adding the causality to the neural networks that could identify which features are important for the prediction results. Here is the pipeline of this project. We first preprocess the lobster stock limit order book dataset, then feeding our model to make predictions of the the mid-price direction. I'm going to introduce the model first, then the data preprocessing part, and finally the results. Our model combines convolutional neural networks and long short-term memory. The CNN is for capture the relation of features. Although CNN is well known for image processing tasks, it is also suitable for our problem due to the structure of our data. As our data are time series, the LSTM is for capture the time dependency. We are also going to add causality on the LSTM layer to analyze the relationship between features and output. Next, I will go through the input and the specific model structures. Analogy to the image that usually have 3 channels RGB as input, we transfer the limit order book data to this shape with 2 channels, the volume channel here in blue and the price channel here in gray. For each channel, the columns are the price and volume from ask level 1, bid level 1 to ask level 20 and bid level 20. And the rows are the events in the time order, just as the original limit order book data. We formulate the data as this shape for the reason that it's more convenient to extract features than the original data. And the input is fed into the convolutional layers. For the convolutional layers, we use 4 kinds of filters to extract different kinds of features. We choose these features because they are considered as useful from previous studies of limit order book data. In these pictures, the deeper blue squares represent the shape of filters. The first one, convolute across 2 channels. It combines the price and volume of each ask and bid level. The second one combines ask and bid level, ask and bid price and volume in the same level. These 2 come from the concept of micro price, which is the average of ask level 1 price and bid level 1 price weighted by their volume, which is an important indicator for the price movement. The third one combines 3 consecutive levels of ask or bid prices and volume. The fourth one combines the features of consecutive orders, which could capture the local interactions among data across time steps. Also makes the shape suitable to feed into the LSTM. Here shows our model structure. We feed the input data into the CNN, which have 5 layers. The first layer uses the first kind of filters that combines volume and price. Here 1 times 1 is the shape of filter, and 32 here is the number of filters, and group equals 2 means we convolute across the 2 channels. The third layer we use the second and third kinds of filters to capture the ask and bid price and volume. Then we stack them together. The rest of layers use the fourth kind of filter that combines the consecutive time steps. We then feed this, as you can see from this structure, we then feed this data into the LSTM layer, after which is a fully collected layer to 3 categories, which we will define later. The CNN generates an embedding of limit order book data to feed into the LSTM. We do not use padding or pooling, so it is clear where these embedding features come from. We want to find out which of these features are useful for mid-price trend prediction. So this is why we add causality in LSTM layer. We consider the Granger causality of time series. Granger causality quantifies the extent to which the past activity of one time series is predictive to another time series. Granger causality in time series analysis usually studied in the vector autoregressive model, and here the VAR. In this model, the time series at time t, the xt here, is a p-dimension vector. It is assumed to be a linear combination of the past k lags of series. Here the AK is a p times p matrix that specifies how lag k affects the future evolution of the series, and the ET is a mean zero noise. In this model, the time series J does not Granger cause the time series I if and only if for all the Ks the AK ij, that's the ij's element of this metric equals to 0. A Granger causality analysis in VAR thus reduced to determine which values in the AK are zeros over all lags. In high-dimensional settings, this may be determined by solving this group loss regression problem here. Here the norm on A is the L2 norm, which acts as a group penalty jointly shrinking all the values of A1 to AK to 0. And the positive number lambda here is a hyperparameter that controls the level of group sparsity. And the Granger causality can also be defined on nonlinear models. The nonlinear autoregressive model here allows time series xt to evolve according to more general nonlinear dynamics. The xti is the ith component of xt. The gi is a function that specifies how past k-lags influence the series I, and in our case, the gi is the neural network. In this context, the Granger non-causality between the two series j and I means that the function gi does not depend on the past lag of series j. This objective function is a single layer LSTM with group loss penalty, as I mentioned in the linear case. The W is the weight matrix of the input, while the U and WO are the weight matrix of the hidden unit in LSTM. The optimization method we use is the general iterative shrinkage and thresholding algorithm. And this algorithm solves this minimization problem with the objective function if W equals to LW plus RW, where L is a Lipschitz continuous function and R can be non-smooth and non-convex. But it has to be able to written as the difference of two convex functions. Our problem is a special case of this algorithm, in which the function R is the L2 norm and the function L is the loss of neural networks, and W are the parameters of our LSTM layer. This algorithm iteratively updates the variable W under the monotone line search condition, and the iteration converges to a critical point, which means the point such that the subdifferential of the objective function equals to 0. Thus, a local minima of the objective function. We compare our model with the baseline model, which is the model in the third paper I listed before. The left-hand side is the structure of the baseline model, and the right-hand side is the structure of our model. The baseline model is a combination of CN, LSTM, and an inception module. The inception module, as you can see from the visualization of the baseline model, is this part that separates to three layers and stacks them together in the few next layers. Our model different from the baseline model that first of all, the CNN of baseline model have 9 layers and an inception module that is rather heavy to train, while our model only has 5 layers. Secondly, our CNN has more kinds of filters than the baseline model that could extract more potentially useful features. And thirdly, we add the Granger causality on the LSTM layer, which could make the model more explainable by identifying which features are important for the model prediction. So this is about the model introduction. Next, we will talk about the data preprocessing part. This includes the labeling and the normalization of data. Different from common classification tasks that we have a clear definition of labels. Here we need to define models ourselves for each sample in the limit order book data mid-price trend prediction problem. We have three classes: down, stationary, and uptrend. We label our data by comparing the average mid-price change, the LT here, with a threshold alpha. As you can see in this formula, and the MT plus is the average mid-price of the future 10 time step of time step t, and MT minus is the average mid-price of the past 10 time steps of the time step t. And if LT is less than minus alpha, the sample at time step t is labeled as downtrend. If the absolute value of LT is less than the alpha, it is labeled as stationary. Otherwise, it's labeled as up. The threshold alpha here is a positive number. If alpha equals to 0, it would result in only two classes, up and down. This kind of labeling is rather noisy because the samples with LT that are extremely close to 0 could be difficult for the classifiers to train. In previous studies, the threshold alpha is a constant for all stocks, but in our datasets, we find that a constant threshold could result in very different distributions of the sample classes. So we choose different threshold alpha for different stocks. We choose threshold that let the sample size balance for the three classes, which means the sample size of three classes are quite similar, as we know that class imbalance could make classes to be under or overrepresented, which could lead to poor results of the classifiers. The purpose of normalization is to make the features in the similar scale, since if features have quite different scales, it could cause the bias during training. For the data normalization in this project, we do normalization separately on price and volume, but do not separate on each level ask and bid, because if we do normalization on each feature, it could distort the order of the ask and bid levels. For example, the lower level ask price must be lower than the higher level ask price, and the ask prices must be higher than the bid prices. Here are the three common ways of data normalization. The z-score normalization that makes the data point centralized. The min-max normalization makes the data point fall into interval 0 to 1. And so does the decimal normalization that choose the smallest positive integer k to let the data fall between 0 and 1. One thing I need to emphasize is that we did not strictly follow this normalization formula in case to avoid using future information. As we normalize the data by day, so for the coming data in the new day, at any times of the new day, we do not know the mean or max or mean of the data in the whole day. So we use the data of the previous day to calculate the mean, max, or the mean to normalize the data. I originally noticed from the training process that our model tend to be overfitting a little bit quickly, as the accuracy of training set tends to be much higher than the testing set. We apply the model smoothing in our training process because the label smoothing could deal with the overfitting as well as overconfidence. And this approach requires the softmax activation on the penultimate layer and the cross-entropy loss in the model. The label smoothing is basically this formula. The alpha here is the positive constant, which is often set at 0.1. The capital K is the number of classes. Yk here is the binary indicator in the cross entropy loss. We can see that the new label is a weighted average of the original label and the uniform distribution. We then use the modified label YKLS in the cross entropy calculation and optimization. For the reason why the label smoothing could work for dealing with overfitting and overconfidence, a study shows that the label smoothing encourages the activations of the penultimate layer to be close to the center of the correct class and equal distant to the center of the incorrect classes, so it's sort of balanced. So then I'm going to present our results on the mid-price trend prediction. First on the benchmark dataset and then some lobster dataset. The benchmark dataset we use is a dataset produced by the second previous work I listed. It contains the linked order book of several stocks traded in the Nasdaq Nordic from June 1st, 2010 to June 14th, 2010, which is a 10 working day period. As you can see from the chart, our model have slightly better performance in terms of accuracy and F1 score. And label smoothing also increased the model performance a little bit. Before presenting our results on lobster dataset, I'm going to show you an overview of the dataset we're using. We use linked order book dataset of 5 stocks, Apple, Google, Microsoft, Intel, and Amazon from the 13th of June to 24th of June 2019. This chart shows this also shows the threshold we choose for the and the number of labels in each class for each stock. As you can see, the thresholds are different, and we find that the number of samples in classes vary a lot when even an extreme small change of the threshold is happen. So the threshold is sensitive in this task. And compared to the benchmark dataset, the lobster dataset is much more up to date, and as the benchmark dataset is from 9 years and 10 years ago. Also, the lobster dataset have much higher frequency, as the benchmark dataset has around 50,000 events in a single day. This lobster dataset have around over 300,000 events in a single day. And these are the results on the Amazon stock. The first chart is the accuracy, recall, precision, and F1 score results of the models using z-score normalization. And the second chart is the result of min-max normalization. We can tell from the results that the min-max normalization has much better results than the z-score normalization on this stock. These are the results on the Apple stock. We can see that the label smoothing can improve the model performance in a quite high range, and the z-score has slightly better results than the min-max normalization in this stock. These are the results on the Google stock. It's similar with the results on the Amazon stock. And this is the results on the Intel stock. And this is the results on the Microsoft stock. From the results of about 5 stocks, we find that firstly, our model generally have better performance than the baseline model. Secondly, the label smoothing can generally improve the model performance. And thirdly, the min-max have better results than z-score normalization in majority of cases. To sum up, I would like to highlight some points that I find useful in this project. First, additional information such as volume and historical prices are useful for mid-price trend prediction, and the results show that the prediction accuracy are generally about 60%, which is significantly higher than random guess, which is roughly about 33%. Secondly, in tasks that we have freedom to define labels by ourselves, we could look for ways that could possibly make the models work better. In our case, as well as in many other cases, the class balancing is a point to be taken into consideration. Thirdly, the structure of CNN has an influence on the results, and it is not the more complex the structure, the better the performance. One possible explanation is that the CNN in our model extract more kinds of possibly useful features than the baseline model. We haven't got the final results of the feature causality yet, because there are some adjustment of some parameters that need to be done. At last, notice that the min-max performs better than z-score normalization. This is probably because that the min-max normalization does not change the symbol of the criteria in our label definition, the LT. That we compare to the threshold, while the z-score does, because the extraction of min may change the symbol of the criterion LT. So that's all for today. Thanks for listening. If you have any questions, please feel free to ask.